Dear students, today we discuss about the phase transitions of pure substances like single component system like water and carbon dioxide. Before getting into the phase diagram of those materials, let's discuss what is phase. So phase is a phase is a form of matter that is uniform throughout in chemical composition and physical state. For example, if we take water, the chemical formula of water is H2O, irrespective of whether it's a solid phase or liquid phase or gas phase. So it's a one component system. So even in solids, you can have multiple phases. For example, take the mixture of allotropes of phosphorus. It can exist as white phosphorus P4 or black phosphorus. Okay, these two are different in its structure because this is a molecule and this is a extended structure, honeycomb structure. Similarly, the polymorphs of calcium carbonate. So these are all two different phases. Let's take the sodium chloride solution. So if you take sodium chloride dissolved in water, you get sodium chloride solution, which is actually a single phase, because if you take any tiny volume from this solution, the composition is going to be same irrespective of the space from which you choose this tiny volume. But on the contrary, if you take the mixture of ice and water, this is a two phase, because the way water molecule are arranged in ice is very different from the arrangements in water. Let's consider the calcination of calcium carbonate. The calcium carbonate solid, when you heat it, it becomes calcium oxide solid. These two are definitely two different phases because their crystal systems and their compositions are different. And you have carbon dioxide gas. So certainly this gives you three phases, two solid phase and one gaseous phase. So if you compare the mixture of metals and their alloys, the mixture of two metals is two phase because they are not atomically mixed. That means they are immiscible. Okay, but if you make the alloy out of them, so if you take again any tiny volume from that alloy, the composition is going to be same. Therefore, the alloy is a single phase. The similar line, if you consider dispersion, where the grains or droplets of one substance present in the matrix of the other, it's a two phase because by the same logic, if you take a very tiny volume from this dispersion, it could be either this droplet of one substance or it is a matrix. So what's a phase transition? Phase transition is a spontaneous conversion of one phase into another phase. Okay, it occurs at a characteristic transition temperature for at a given pressure. Okay, so at this temperature, the phases which are involved are in equilibrium, and the Gibbs energy of the system is a minimum at the prevailing pressure. Let's take an example. Take ice at 1 atmospheric pressure. If you maintain the temperature below 0 degrees C, it will be stable. If the temperature goes above 0, it will be in liquid phase. Okay, so that means at temperature less than 0, the Gibbs free energy decreases as the liquid water changes into ice. Similarly, when you go temperature above 0, slightly above 0, the Gibbs free energy decreases as ice changes into liquid water. So what's chemical potential? So in the previous class we have seen the definition of chemical potential. So chemical potential of a system that consists of a single substance is nothing but the molar Gibbs free energy, right? Gm or G bar. You can define chemical potential in a different way. At equilibrium, the chemical potential of a substance is the same in and throughout every phase present in the system, or the chemical potential of a pure substance in two phases like ice and water in equilibrium are equal. So how do you detect a phase transition? If it involves apparent change, for example, ice to water, you can clearly see the solid and the liquid phase. It's very easy to detect. But there are some phase transitions uh, which involves two solids, say solid 1 and solid 2. For example, the phosphorus, white phosphorus and black phosphorus kind of thing. So how do you detect the phase transition? For that we need to use something called thermal analysis. So the thermal analysis takes advantages of the heat that is evolved or absorbed during a transition. Okay, so that's if the phase transition is an exothermic process and the temperature of the sample is monitored as it cools, the presence of transition can be recognized, okay, by the pause in the otherwise steady fall of the temperature. Let's see this statement with an example. Let's take the say water in liquid phase. So as you cool it, the temperature of the water falls until it hits a particular temperature called the freezing temperature. At that temperature, the liquid continuously turns into solid. It's called freezing. Until last drop of the liquid turns into solid. So you will have this freezing event going on without change in the temperature. Once all of them converted into solid, then again the temperature of the solid phase start decreasing with time. Okay. Is there any other method to monitor such phase transition? Yes, we can have in situ X-ray diffraction methods, wherein when you heat a sample or cool a sample, if it undergoes a phase transition, so from one crystal system to another crystal system, so the XRD pattern of those two phases would change. From that we can recognize there's a phase transition. Let's consider the equilibrium between the liquid water to vapor, and say dN, a very small quantity of moles of water goes from the liquid phase to gas phase. So what is the Gibbs free energy of this system? It's a combination of Gibbs free energy in liquid phase plus the Gibbs free energy in the gaseous phase. This is constant temperature and pressure. So this can be written like this in this form, differential form. So if you look at the number of moles that left the gas phase is nothing but the number of moles that landed in liquid phase. Alternatively, the number of moles which left the liquid phase is what which reached the gas phase. So using this relation, we can modify this equation as I have shown here. So this quantity here is for a single component system like water. It is nothing but the chemical potential. So chemical potential of gas phase minus this chemical potential of the liquid phase into dN. But we know at equilibrium the dG is 0. So if this is 0, and we know this cannot be 0 because this certainly some amount at equilibrium moves from the from the liquid to gas phase or in the reverse direction. So this quantity here must be set to 0. In other words, at equilibrium, the chemical potential in the gas phase is equal to the chemical potential in the liquid phase. So what happens, suppose if the temperature and pressure are varied? Okay, so this we can understand considering two hypothetical phases, say alpha and beta. So the chemical potential in alpha phase is this at constant temperature and pressure, and the chemical potential in beta phase is this. So when they are in equilibrium, alpha and beta, so the chemical potential in these two phases are equal. So now we apply the condition of varying pressure and temperature, so you get this equation. But we can use Maxwell's relation. Okay, we know dou G by dou P at constant temperature is V, dou G by dou T at constant pressure is minus of entropy S. Okay, so but for a pure substance, so this quantity G is nothing but the chemical potential. Okay, so this becomes dou mu by dou P at constant temperature, which is nothing but the tiny change in the the molar Gibbs free energy by dou P at constant temperature. So this is equal to molar volume. So substituting these molar volume and molar entropy into this equation, so we arrive at this particular equation here. And again, using this relation, we can reach this equation wherein the dP by dt is nothing but the delta H bar transition divided by temperature into delta V transition. This is called the Clapeyron equation. In the next video, we will see the phase diagram of water and the carbon dioxide system. Thank you.